Hey, Mr. Sands, we're just about done with these podcasts.
Yay!
Yeah, so, hey, we have that word.
Stoichiometry.
We are going to do stoichiometry and gas laws. We're going to
Wait. Pause. Okay, I think they're done groaning now.
Okay.
Yeah.
Hey, the other thing you're going to need, guys, is your calculator.
Yep.
This is like the math portion of the
And
chapter.
you should also get
well,
out
actually,
your...
it's already been mathematical.
That's
hasn't
true.
it?
Yeah, you should also get out your mole map.
Mole map. Yep. Yeah, we're going to do some stoichiometry. We're going to combine it with gas laws. So, hey, let's get going. Hey, gas laws and stoichiometry. All right. The problem that we've been dealing is whenever we've done math with gases, we use that cool number, 22.4 liters in 1 mole. And that works great if you're at STP.
Most places aren't at STP.
And you know where we live? It's never at STP.
Never. Yeah, if you live like in Boston in the wintertime, you might be at STP.
But we're never here at STP.
No, our pressure's too low.
We have low pressure. So
we get the temperature right.
So we have a problem. So standard temperature pressure, as you recall, is 0 Celsius, 1 atmosphere. And you could use that 22.4, but only if you're at that temperature and that pressure, which is just not going to happen very often. So there's 2 ways to solve these problems. Okay. You can, A, number 1, do some stoich, and then do Pivnert.
Okay.
Or B, do Pivnert, and then do stoich. It sort of depends on the question. You'll see. It's just very simple.
It depends on what you're starting
PV
with.
equals nRT is your equation. You're going to use this like over and over. We've done this before.
We have.
Now we're going to mix it with stoichiometry.
Yeah. Now, if you look in PV equals nRT, what's the one thing in PV equals nRT that's common to what we've been doing in stoichiometry? That's N, moles.
Yeah.
Stoichiometry always boils down to moles. So we're going to use the N part of stoichiometry
with the ideal gas law, you mean? Yeah.
Right, of the ideal gas law, right, for
to
stoichiometry.
Do stoichiometry. So we're going to do a couple of examples, Mr. Sands.
Alrighty.
Hey, we have a problem sitting in front of us. So, hey, potassium chlorate. All right, I don't have the formula of this.
No, we should probably write that down.
Potassium. As you recall, potassium is K. We're going to put the charge game is positive. Chlorate is a polyatomic ion. Look on the back of your periodic table.
ClO3.
ClO3, and the charge is negative
-1.
1. That's an O. All right. Decomposes into oxygen gas. Actually, KClO3. So we'll write KClO3. Why did I write 1 K and 1 ClO3?
Because +1 -1, they adds up to 0.
And it decomposes. So that's just a stinkle arrow. And it makes oxygen gas. Oxygen is a little tricky. It's O2.
Brinkelhoff.
And it makes potassium chloride. Now, chloride is Cl -1. And that's going to mix with potassium.
So KCl.
So that's KCl. Now, that's an unbalanced equation.
It
is.
is.
Balance it. I have an O problem. I have 2 O's here and 3 O's here. So I'm going to do the 6th thing. Right? I need to put 3 here to get 6 and 2 here. Messes up my potassiums and my chloride, so I put a 2 here.
Yeah.
So start with a balanced equation.
Okay.
So now what do we know? When we have 3¼ grams of potassium chloride, that's 3.25 grams. Write down what you know underneath what you know. Decomposes at 610 torr. Now, we're measuring the gas. The gas here is oxygen. And so this pressure is 610 torr.
We have a temperature.
We have
34 Celsius.
Temperature is 34 degrees Celsius. And it's asking what is the volume of the oxygen gas. So
we have almost enough stuff to use at PV equals nRT.
We need N, though.
The one thing we're missing is N, but we can get that from stoichiometry.
So I'm going to take this 3¼ grams and convert to moles of oxygen gas. So watch what I do. I'll say 3.25 grams of KClO3 over 1.
Now, don't tell me you know the molar mass of potassium chloride off the top of your head.
122.5, Mr. Sands.
What?
Grams of KClO3.
Holy cow! Good grief!
To 1 mole.
You're a freak of nature.
KClO3. If
Should
you
not
add
know that.
K plus Cl plus 3 O's, it adds up to 122.5. Doesn't everybody know that?
They do now.
They do now. Mr. Bergmann knows it. How did we get that? We added K plus Cl plus 3 O's. I did that in my head as I was sitting here talking. Not really. I just have it memorized. All right. And then the the grams of KClO3 cancels. And now I need to put the mole
ratio
of KClO3 to the moles of oxygen gas. And there are 3 moles of O2 from the 3 the balanced equation and 2 the balanced equation here.
Okay.
All right, so that gives me the moles.
So we got some math. We got 0.0398
moles. Good.
moles.
Now,
put that in.
that's N. So N, well, that's just equal to N.
Yeah.
So we're going to do PV equals nRT, and we're going to solve for V.
Right, and we have to do a little bit
we have
of-
an issue here. Pressure
Yeah.
is 610. We'll just divide that by 760, right, to get our atmosphere point something.
0.803.
803, the ATMs. And temperature, we'll add 273, and we get
307.
307. And so now I'm going to plug my numbers in. I'll do that down here, I think. So the pressure is 0.803. That's P. That's a P. V is my X. Equals N. N is 0.0398 times R. R, remember, that's our constant, 0.0821. And my temperature is 307. Simply divide everything by 0.803.
And you get V.
And you get V. And you get V to be what?
1.25
liters of oxygen gas. So you'll produce in this reaction this many liters of oxygen gas.
All right.
Notice what we did is we did some stoichiometry first. That was this part down here. And then we plugged it into the ideal gas law. Well, let's do it in the backwards way, Mr. Sanders.
Okay.
So let's do one more example. Example number 2. Copper 2 oxide reacts with carbon to make solid copper and carbon dioxide. We got to write a balanced equation. Copper 2. Roman numeral. What does that mean?
That's the charge.
Charge! Cu plus 2. Oxide is O negative 2 with carbon. So we're going to have
CuO.
CuO plus carbon to make solid copper.
Cu.
Cu.
Later.
Plus,
that was dumb.
oh, good, yeah.
Yeah.
Plus
Don't ever let me do that
carbon
again.
dioxide. I won't.
Okay.
That's it.
Okay.
Is that balanced?
So what do we...
No, not
balanced.
I've got an oxygen problem.
Yeah.
So I'm going to put a 2 here to get 2 oxygens because of the CO2. And I would put a 2 in front of the copper.
There we go.
So now what do I know? All right, I have carbon dioxide. I know I have 34.5
Milliliters. That's a volume.
That's a volume. So let's put a V there.
Okay.
And actually, you know what I'm going to do right away?
Let's just make it liters.
0.0345 liters. Divide by 1,000 in my head. My pressure is 655 torr. Oh, we
Let's
have a problem.
make that change, too.
We can't change it yet, Mr. Sands, because it's collected over water.
Oh!
If it's collected over water, we must refer to the
table.
The water vapor pressure table.
I bet you have
We've
that.
got to find. Oh, I bet I could find. There it is.
What temperature were we
I don't
at?
know.
Now we
What
have to go
temperature
back.
were
See,
we
got
at?
so excited.
I know. 32 Celsius.
Celsius.
So at 32 Celsius, the pressure is 35.
35.6.
We'll call that 36 because I think we've got it to.
36.
So we'll subtract 36, and that equals, Mr. Sands,
619.
619 torr. And while you're at it, divide that by 760, and we'll get our ATMs.
0.814.
814. All right, PV in, we don't know.
We don't know. We'll get
but
that from...
we do know our temperature. That was 32 degrees Celsius plus 273 is 305, right? Yeah.
Yes.
305.
No, wait.
Yeah, that's right. 305 Kelvin.
Yes.
So we have everything to do the ideal gas law.
Right. So last time we did stoic first, and then we did PV equals nRT.
So, yeah, let's talk about what you're going to do. Once you get in, we're going to solve for in just a minute. You're going to use stoichiometry, and you're going to, actually, we didn't actually put this here, but you're trying to find the grams of copper 2 oxide. You're going to convert to the grams of copper oxide using stoichiometry.
So PV equals nRT first, then stoichiometry.
Yeah. So
last time we did stoichiometry, and then PV equals nRT.
So let's do our PV and RT.
All right, let's do it.
P is 0.814. I'm not going to put the units in there. V is 0.0345 equals N. We don't know that. R, of course, 0.0821. Notice I'm just plugging in my numbers, and my temperature is 305. When you get N is what, Mr. Sams?
1.12 times 10 to the negative third.
And that's moles of oxygen.
Carbon dioxide.
Carbon dioxide, I knew that. Okay. So this is my starting number I'm going to put in my stoichiometry. So I'm going to say 1.12 times 10 to the minus third moles of CO2. Now I want to go from moles of one substance to grams of another. So the moles of the CO2. Now I do have I'll use my mole to mole ratio. So I'll say 1 mole of CO2. Now that 1 comes from the 1 in the balanced equation right here to 2 moles of carbon copper oxide, copper 2 oxide. And now I'm going to use the molar mass of copper oxide, so 1 mole of CuO to so many grams of
79.5.
And that's 79.5. So we're going to, moles of CO2 cancel, moles of copper oxide cancel, and we take 79.2, pretty small number.
No, it's a
couple of grams. No way, Mr.
Got
James.
it. No, I must have done something wrong. 79.5
times 2
times 2
times 1.12 e negative 3
times 2. I must have hit the divided by sign. There we go. 0.178.
0.178 grams of CuO.
There we go. That's
So
it.
notice what we did. We did PV equals nRT, solve for N, and then we did, that was this whole step right here, and then we took the N and did a conversion down here and converted the moles of carbon dioxide to the grams of copper to oxide. So you're going to do lots of problems like this, and this is going to become like second nature. We just wanted to give you 2 quick examples so that you can know how to do it. You may need to watch this several times.
Well, hopefully stoichiometry is already second nature to you.
Yes. Okay.
Whoops.
I think I hit the button or something
I think you
like
did.
that. Okay. So that's it, and we will see you in class. Bye-bye. See ya.
Don't break any flasks.
Yes.